Good afternoon, everyone. Welcome to the DDR3 and 4 webinar hosted by Microlease. My name is Nicole Crossman. I'm the East Regional Manager for Microlease, and I'll be getting us started. Let's go to the agenda. We're going to start off with a quick introduction to Microlease and then jump right into our DDR content. We'll talk about some DDR product solutions that are available, have a 10-minute Q&A, and a 5-minute wrap-up. Microlease is the fastest growing test and measurement rental company in the world, and we're already #1 in Europe. We have a large inventory of cutting-edge technology to meet your application needs, and most of them available for immediate rent at highly competitive rates. We're a total solutions provider with several ways to acquire test equipment. As I mentioned, we rent equipment. We also lease equipment, whether it be a capital lease or operating lease. We sell refurbished equipment, new equipment, and we're an asset management company. With our refurbished equipment, you can get current products at reduced prices, save 25 to 70% off manufacturer list prices. We have new equipment from leading manufacturers such as Agilent and Tektronix, some of which we'll talk about today. And we're also an asset management company. With our Leo asset management software, you can get complete visibility into the equipment you own and its utilization. We have over 4,000 product lines to rent, lease, or buy. Most of them are in stock for immediate delivery in our warehouses in the US and Europe. $400 million in inventory, and we manage 20,000 assets daily. Now, some of you might be new to the name Microlease. Well, Metric Test was acquired by Microlease in October 2011, and just recently, we've taken over the Microlease name. Here are some of our manufacturers that we represent. Leading brands such as Agilent, Tektronix, Advantest, JDSU, Anritsu, Keithley, Rohde & Schwartz, Instex, Chroma, and Fluke. We have global service capabilities with offices and inventory throughout Europe, North America, and Asia, over 250 employees worldwide, and we service over 85 countries. Now we're going to get right into our DDR3 and 4 webinar presented by Tom Purdy. Tom is a senior applications engineer specializing in HDMI, DisplayPort, MIPI, PCIe, and DDR applications. For over 30 years, Tom supported digital test applications at HP and Agilent, where he also led technical training for Agilent sales force. Early in his career, he designed and tested microwave antennas. Tom has also served as a senior test consultant to firms in the Bay Area and continues to lead digital application testing. Currently, he's a consultant at Granite River Labs and for Microlease, and he provides test services for us and helps our customers with configurations and applications. So with that, I'll leave it over to Tom.
Well, good afternoon. If for some reason you can't hear me okay, please feel free to send a text comment. Otherwise, I'm going to proceed. And I guess, thank you, Nicole. I really don't have anything else to say about myself since you've kind of covered the whole waterfront. Anyway, let's get started. Today, what I'd like to do is give you an overview of some of the most important things when you're thinking about looking at DDR signals, primarily in the physical layer, although we will talk just a little bit about looking at the protocol layer. So on this slide, we're kind of looking at the history of DDR, and I would imagine when people first started using this, they had no idea that we were going to be pushing this, what is basically a parallel bus with single-ended signals up into the range of 3 gigatransfers per second. But that's where we're headed to today. And so back in the old days, when it was 100 megatransfers, people didn't worry so much about what the traces looked like on the board. They were simply a way to get signals from A to B. But as we get above 1 and 2 gigatransfers, suddenly we really have to think about those traces as transmission lines, and we've got to think more about what they look like as a microwave design problem, and not simply just as how do we get digital signals across a bus and how do we decode them. Okay, I think you probably are all aware of where we're headed, so let's move on. I want to give you a little background on some of the things that changed when we moved to DDR3 and then when we moved to DDR4. So in DDR3, of course, the data rates are between 800 and 1600 megatransfers per second, and the address command bus is basically half of that rate. Starting with DDR3, there was a requirement to make the data strobes differential in order to improve their fidelity. It's much easier to transfer a high-speed signal on a differential pair than it is on a single-ended line that's referenced to ground. And another thing that was added in DDR3 was the ability to make on-die terminations change dynamically depending upon whether you're performing a read or a write in order to better optimize the impedance of the transmission line for those two different states, depending upon which end of the line is driving the signals. And also, we were able to set separate cast latencies for reads and writes in order to optimize the timing and the utilization of the bus. And another important change was the topology of the address and command bus changed to what we call a flyby architecture, which we'll show you in the next slide. So on the top is the kind of the old way of doing things, which is the command and address bus signals come in and then they fan out in a kind of a T arrangement to all the different DRAM chips on say a DIMM in this case. And that has an advantage of being able to kind of manage the time delays to make them all about the same to each memory chip. It has a real disadvantage in terms of signal integrity because the signals are now looking at really severe mismatches where every place you got a T. So with DDR3, what they call flyby routing was used instead, and basically the command and address bus comes in along one side and then gets daisy chained through the chips over to the other side. This allows for much better management of the impedance of that bus and less reflections, better signal fidelity, and the only issue is that it takes longer for a command and the address to get to the last chip on the line than it did the first one. But the memory controller does, in its initial power-up and training sequence, determines what those differences are and keeps track of them so that when data comes back from, say, several chips all at the same time, it can clock them in based upon what the optimum position is for each chip. Okay, so let's move on and talk about the changes that occur with DDR4. Now we're talking about doubling the data rates again from 1600 to 3200 mega transfers per second. One thing to notice at 3200 mega transfers per second is that the data valid window is really pretty small. A unit interval at that rate is about 300 picoseconds. So if you're going to optimally sample that data 90 degrees right in the middle of the data, you're talking about something that's about 75 picoseconds wide. And that's a pretty small window when you think about noise and jitter and other things that can shrink that window. So in order to make sure we're sampling the data at really the optimum place, we go away from using default values for setup and hold, which were used in the earlier like DDR and DDR2 schemes. And instead, during initialization of the memory controller actually goes off and determines through a kind of a training sequence, much like you might find in PCI Express and some serial interfaces, what the optimum time and voltage position is to sample the data coming on each data from each memory chip. couple of other changes. Basically, the specifications are designed around assuming a 1e to the minus 16th bit error rate, which is a pretty tight standard. And the standard does allow for vendors to advertise a lower bit error rate and then use the wider limits that would be associated with, say, 10 to the minus 12 or 10 to the minus 14th. While the architecture of the command and address bus didn't really change very much, a parity bit was added, largely to avoid the possibility of say, sending data in a write to an incorrect memory location, something that would be pretty much unrecoverable. So anyway, I would probably ask for questions at this point, but we can't do that, so please send them in the chat line, and we'll get to them at the end of the seminar. Okay, so we've talked a little bit about what changed with DDR3 and 4. I'd like, since we're going to kind of focus on the physical layer, I'd like to talk just a minute about how much bandwidth you might need in a scope. For looking at the different technologies, across the top here we've got all the way up to DDR4. And what we've done is taken the maximum slew rate that's allowed in the JEDEC spec along here and the typical voltage levels and calculated what probably the worst case or the steepest rise time might be for any of these technologies. So keep in mind that while these projections show, particularly for DDR4, that you might need some pretty high bandwidth to look at it to get really high accuracy, the actual bandwidth you need is more dependent upon your particular application, both the devices and also the traces that are involved, because, you know, a couple centimeters of passing a signal this fast across FR4 are going to filter it to a much lower rise time. But anyway, to complete the picture, we came up with what would be probably the highest frequency component you would need to capture in order to get a fairly reasonable picture of the waveform by using this formula that actually was created a long time ago by a man named Howard Johnson. It's a pretty good rule of thumb. Another way that many people do it is to take the data rate. Say, let's take 2000 megatransfers per second, divide it in half, and that would be your fundamental frequency. What you'd see if you made a frequency measurement on alternating ones and zeros. So then multiply that by 5 to get to your fifth harmonic. That would say probably you'd need around a 5 gigahertz scope. If you did that here, you'd say, well, I don't really need 15 gigahertz. It's kind of a function of the rise time, as I said before. But in any event, in most cases for DDR3 and probably DDR4 applications, a scope that's somewhere in the 8 to 12 gigahertz bandwidth is going to be what you need. And if you're really trying to get the best picture you can of the rise time, for instance, or an eye, and you do have really steep edges where you're probing, then maybe you do want to look at a 20 gigahertz or a 16 gigahertz scope. These numbers down here basically come from empirical measurements that have shown that if you multiply the max frequency by 1.4, your rise time measurements should be within about a 3% accuracy, and it would be about 10% if you multiply by 1.2. I didn't put it on here, but you get about 20% accuracy if you just go with F max. Now that applies to a rise time measurement. Other measurements are probably less sensitive. And again, this is kind of like worst case picture. If you just want to look at some signals, DDR3 signals, you could actually use a 4 gigahertz scope. You just probably can't trust some of the measurements like rise time and what the eye exactly looks like. But for a quick and dirty look, that would be adequate. Okay, so now let's talk about how are we going to actually look at these signals. And the first thing we have to pay attention to is the fact that on a bus we have both reads and writes. And we're going to somehow have to separate the reads and writes if we want to make meaningful measurements on, say, the data lines. So just a quick refresher. On a, the DDR data bus is bidirectional. The DQ signals travel from the memory controller to the memory in a write, and because they're coming out of the memory controller, it has the circuitry that allows it to offset the DQS, the strobe, into the middle of the data valid windows, which is the right way to send data from one place to another. So you always know you have a write when the DQS's edges are centered in the middle of the data valid windows. Now the reads come back from the DRAM chips. They're meant to be inexpensive and not have any extra circuitry that isn't really necessary, so they simply clock the data out on the edges of the strobe. So you can tell a read basically when the clock and the data edges line up. Okay, let's move on to the problem. So here's a scope showing read and write bursts. And on the left, we have the green is the DQ edge, DQS. I think it's actually the yellow. And the DQ is the data itself. And you can see that the edges really line up on top of each other. And as we go over here on the right, you can see that the strobe and the data edges are actually offset from each other by 90 degrees. And this kind of messy, undetermined state in the middle is basically when the bus goes to a high impedance state and the signal's just floating. So here's the problem. We're looking now at a data strobe, and we're also looking at a DQ line on a scope with some persistence so we can make some eye measurements. And this is really a mess. We don't know how to find an edge to make a measurement on. So we're going to walk through a couple of different ways to separate out the reads and writes. Not that one of these is better than the other. It just simply, I'd like to give you some techniques that when you go and put your probes on a couple of signals, you can maybe figure out which ones are reads and writes. Okay, first method would be to look at the preamble, and if the preamble is different between a read and a write, then it might be an easy way to trigger on it. So let's see if I can go back here. In this slide right here, what we're seeing is the alternating high and low states of what should be a clock signal. And then behind it, you can see a preamble, and there's actually two of them here. And if they were different in width, then what we're talking about is making a trigger that senses the width of the preamble and then picks the reads from the writes out of this. It's a possible solution. It kind of only works really well if you do have signatures for the two preambles that look a lot different from each other. Another method, which is really probably the easiest thing to do, is to just simply adjust the trigger level to the point where it's up above one set of bursts and within the range of the other set of bursts. Now this is a picture of reads and writes, and probably taken close to a DRAM chip. So the size of the read signals is actually larger than the writes, as you would expect, because we're closer to the source of the writes. And we're also on the other side of, we might be on the other side of some resistors that sit between us and the data coming from the memory controller. So this is probably the simplest thing to do, and it might be a little more difficult to separate the writes unless maybe you can set up a two-stage trigger that says, I want to find this, but I don't want to find something in this region. But anyway, it's a pretty useful technique. Now another kind of a fancy technique is to use a mixed signal oscilloscope. And a mixed signal oscilloscope, I have a picture of one in the next slide, basically in addition to having 4 analog inputs, has 16 or 32 digital inputs. So if we take advantage of those digital inputs and hook up some signals like write enable and CAS and maybe some address bits, not only can we determine when we've got a read and a write from the RAS, CAS, and write enable, we can pick out what command it is, but we could actually say, well, we want to do a write at a particular address. So it's a pretty powerful tool. Probably one of the disadvantages is you might not have one available. So let's move on. I'll actually show you a picture of one. This is a Tektronix mixed signal oscilloscope, and down at the bottom we see our 4 analog inputs, and we see a cable that's got the digital inputs on it. And what's happened up here is we've taken some of these flying leads and connected them to the different signals that we wanted, RAS, right select CAS, and chip select, for instance. And then we maybe have a data strobe and some data lines hooked up to the analog inputs. What you actually hook up kind of depends upon what you're going to want to trigger on, but it can be a really powerful tool. We'll talk a little more about logic analyzers later and how they compare to MSOs, but let's move on. So the fourth method is what's called a graphical trigger. And basically here, newer scopes have the ability, real-time scopes, have the ability to draw imaginary boxes on the waveform like we've done over here, and then specify whether a trace is supposed to intersect or not intersect that box. So in this case, we've created a zone, and we've said this is a zone that the waveform must not intersect. Agilent calls this zone qualified triggering, and I believe Tech calls it a graphical trigger. But the concept is similar. And so because scopes now have really fast microprocessors in the running windows, and they have DSPs and FPGAs that handle a lot of the display functionality, they can make acquisitions and display them much faster than you can see them doing it. So basically what the scope does is it makes an acquisition, tests it to see whether or not that particular acquisition complies with what you told it to do. And if it does, in other words, there's no trace there, then it displays it. And it captures another one and makes another decision and either displays it or throws it out. And it can do that much faster than you can tell it's doing it. So it looks like it's actually a hardware trigger, but it's really a software trigger. Okay, so all we have to do now to separate reads and writes, once we got rid of the extra traces in here that we didn't need, is to create another zone that is one that the waveform should intersect, and either put it on the top preamble here, in which case when we do that, we see a preamble and an edge that intersects the middle of a data, so we know that we've got a write, or we set it on the lower one here, and we get to look at reads. So anyway, it's really important to be able to separate the reads and writes, because now we could use any of the automated measurements to take, rise time measurements or eye width or eye height measurements, whereas we couldn't do that on this thing here with any reliability. And we've talked about 4 different ways that we might want to do that. Okay. So now what we need to do is talk about how are we going to get to those signals. Oh, I'm sorry. One more nice little feature of real-time scopes. This actually comes from a Tektronix slide. They have the ability to search through a capture, a record of waveforms, and look for particular things and mark them, so that then you can either jump to those with like a 4 next button or actually make measurements at those particular places. Okay, so now I'm sorry, before we talk about how to get to the signals, let's talk a little bit about making measurements on the signals. As I said before, if you just simply want to look at the signals, then you don't need a lot of sophisticated software, and you may not even need, depends upon what you want to find out, a high bandwidth scope. But if you want to determine whether the signals you've got are likely to be compliant with what the JEDEC spec requests, then most scope vendors, and Tech and Agilent in particular, have software packages that do this. So this is an example of the Tech package that basically will acquire a waveform. But first it'll set the scope up to the proper parameters and acquire a waveform and then make measurements on it. The thing that's beneficial about these software packages is that a team of software and hardware experts has actually sat down with the specification and taken the time to understand what measurements need to be made and figured out how to get the scope to make those automatically, verified that they actually do in fact do what's required, and then coded it into software so that you don't have to do all that work yourself. In the case of the Tektronix package, it's called option DDR-A, and it really covers all of the current DDR type interfaces that are supported. And here's an example of a screen where you would specify which technology you're testing and what data rates you're running it at. In a similar fashion, Agilent has also a compliance test suite like this. And again, we have a screen where we tell it what version we're running, what data rate, and I put some part numbers down here. There's not simply one option, there's different part numbers. But those are details you can have us help you with later. Slide, there we go. So I'm going to walk you through what the software packages look like, and this is typical of both packages, although the screenshots are a little different. Basically, you're going to have a screen on which you can select which tests you want to run so that you don't simply have to run all of them. If you want to make a particular measurement over and over again, maybe to make some changes to your device and then retest it to see if you can get it to pass. There's typically another screen where you can modify some of the things the software is going to do without having to rewrite the software. But an obvious thing is maybe you hook the DQ to channel 3 instead of channel 2. Well, you can change it in the screen here. And then typically you're going to get a picture and some words that tell you how you should be connected for the test. Then the scope, the software is basically going to take control of the scope, do all the setups that need to be done in order to ensure we're getting the right signals and the right levels and that we're in the right place in a DDR bus transfer. And then it's going to go off and make the appropriate measurements. And while it's doing that, as it completes a test, it's going to create a table of the results and tell you whether you're passing or failing, and basically what the value was and what the margins are. And in general, at the finish of that, you have the ability to create a report that contains the same information along with some screenshots and the actual values that were measured so that you can actually see what and store the information for the particular device you're testing. Oh, let's see here. So to kind of summarize, basically there's some really powerful software tools available for making measurements on all the DDR technologies that are available. And not only, they do a couple things, as I said before, it spares you the work of reading through the compliance spec and figuring out how to make the measurements. Also, because it sets the scope up and makes the same measurement the same way each time, it reduces a lot of the uncertainty and variations that might occur if we were making these, some of which are fairly complicated measurements manually. Okay, now I'm going to move to the next topic, so if you've got questions, please put them in the chat area. So now, finally, how are we going to get to these signals in the first place, and how are we going to do it without making a mess of them? So now this is an example from what a PC looks like, but basically the structure is the same. We're going to have a memory controller and probably some length of traces. We might or might not have a socket, and then we have one or more DRAM chips to connect to. This is an example where we have the DRAMs mounted on a DIMM card that goes in a socket. So that makes it easy, potentially, to get to the signals at the socket, depending upon what we want to do. But something to note here is that the JEDEC spec actually defines most of the signal levels as if you were making the measurements at the BGA balls at the back of the chip itself. So that actually would be the perfect place to make the measurements. And we'll talk about how to get there in a minute. But let's first talk about a couple of other ways you might get the signals if either you can't get to the balls or you maybe want to just make some more quick measurements. On the left, we have an example of a DIMM card where the vias actually bring the signals from the balls out to the back side of the card. Now, you don't often see that today, but if you did have a case, say on maybe a board where you embedded a single memory chip, then you could simply solder an active probe tip down to a couple signals and make measurements there. Another thing on a DIMM is that they often have some isolation resistors between the edge connector and the memory chips, and you could solder some probes between the memory chips and the resistors, and you get fairly good signal fidelity. You'd be closer to the memory chip, and you would have some isolation from reflections with these resistors. But let's talk about some of the problems with simply intersecting the bus somewhere between the memory controller and a DRAM, which we've done here. We've soldered some solder down probes. They're actually 12 gigahertz bandwidth probes onto the traces going between. So, and these are high bandwidth FET probes, more than 25 kilo ohms of impedance, so they're not really loading this low impedance bus down. But when we look at the signals, the data signals are a little bit ratty. We've got this flat spot here, which could be a potential problem, both to some of our measurements in the analog world and also perhaps to capturing reliable data, particularly if this flat spot was even worse than it is. And that's because we're somewhere in the middle in no man's land, and we're capturing both direct signals and reflected signals, and they're destructively interfering with each other. So sometimes this is the best thing you can do, but it's worth keeping in mind this picture, and if you see something like that, maybe get a browser out, and if you can get closer to the source of the actual data, go over there and probe it and see whether it looks better to kind of eliminate one source of what might be causing that problem. Okay, so now let's talk a little bit about how we would actually get to the signals on the back of a BGA. And actually, this is a slide that summarizes different probing solutions from Agilent, but I'm going to use it as kind of an overview of the different probing solutions. On the left side here, we have some probes that were designed primarily to be used with an oscilloscope. This is a small circuit board that you can see these rows of 3 balls on this side and on this side pads. That's where a memory chip is actually going to get soldered down. The back side of this board has a similar set of pads that would be soldered down to the board where the chip goes. So basically the idea is you put the interposer on the board and the memory module on top of it, and then heat it up so that everything gets soldered together. This probe has a pretty high signal fidelity because it's very small, and it's got little short stubs that connect the signals we're going to look to these pads on the outside where we hook up scope probes, and that's what we see here. You can't see the board anymore because it's underneath the DRAM, but we have, these are really ZIF tips for scope probes soldered to some of these points along here. There are both signals and grounds interspersed here so that we can always get either single-ended or differential signals. Below it is the more typical things you might call out if you're trying to get to a signal really quickly. An active probe, FET probe, and different types of connectors like a browser, solder down probes, and ZIF tips, and so on. Some of these aren't appropriate, but just to give you a flavor. So on the right-hand side, we have a different type of probe that is really more than just a circuit board. It actually has these little flexible wings attached to it. The nice thing about that is the wings will bend up at a 90 degree to get into fairly small spaces. And then along the edges of the wings are where we can connect to the signals. We'll talk more about that on the next slide. In the middle, these are the last two are solutions for connecting a logic analyzer up where you really want to get to the entire 64 bits of data and all the other signals on the bus. This is one example of a connectorless probe, and what we've done on the board is on the traces that go between memory and the controller, we've placed little pads that are positioned to mate up with pins in this connector so that we can access all the signals and take them through this cable to the logic analyzer. Secondly is a DIMM interposer, which is meant to go down to a DIMM slot, and it leaves a socket on the top to plug a memory DIMM into, and then we've got connectors we can hook the logic analyzer up to. As I said before, we'll talk a little more about logic analysis at the end of the seminar. Okay, sticking with Agilent for a minute, then we'll go to Tektronix. This kind of gives you a flavor of how you would use these interposers that have wings on them. On the edges here really are the connectors, and it's a zero insertion force connector type thing that this connector actually mates with. So you take this connector and slide it on the side and flip the little lever to make it stay in place, and you could connect this one to the other side, and now you have through these cables connections that can be connected to a logic analyzer to look at the bus. If you want to hook a scope up instead to these signals, then there's this adapter over here, which again has the ZIF connector that mates with one of the wings, and pads where we can connect solder down probes. So we could solder the probes either to the interposer I talked about before or to this thing here. The difference between these two approaches is this is much more convenient and allows you to switch between logic and scope, but it doesn't have quite as good a signal fidelity as just this small board by itself. Okay, so you might question how this can be a very good solution. It turns out that that little interposer board does not simply have vias that connect the DRAM to the PC board and wires that go off in a T fashion to pads. There's actually embedded in these boards tip resistors, the same type of resistors that are used in most high impedance probes to basically provide critical damping to the probing that sits behind where the probe tip is, so that you don't get resonances and we don't adversely affect the signals we're looking at. And this is true of almost all of the Agilent and Tech BGA interposers. They have embedded resistors that really add significantly to the signal quality of them. Otherwise, it would probably be a fairly sloppy implementation. So another option is actually hidden underneath this. I don't know whether I can move that. Oops, sorry, I can't do that. Anyway, the words are up here. There is another form of interposer, which is a socketed package-on-package probe, which allows you, instead of soldering that sandwich down to the board, actually soldering the socket in interposer down and then putting the memory module in a socket on top of it. Another thing on this slide, kind of unrelated, but in one sense related, is that most of these BGA interposers have electrical models that have been made, S parameter files that can be used by many real-time oscilloscopes. If you add a software package to the scope to allow you to de-embed fixturing, then in the case of Tech, they call them filters, and in the case of Agilent, I think they talk about embedding and de-embedding. But the concept is the same. Basically, you can mathematically convolve the raw data that's been collected from the interposer with the information about what the interposer looks like and come up with what it would look like as though the interposer weren't there at all. So another little trick to keep in mind if you're really trying to get the last little inch out of your measurements and get them as precisely as you can. So here's a close-up of one of those kind of high bandwidth probes that doesn't have the wings on it, soldered down. Now here you can see the pads where the DRAM is going to be soldered down, and you can see traces that go off to some pads along the edges where the scope probes would be soldered, and then there's grounds along the edge. This is just another memory chip next to it. This is a list of things that are supported, or at least when the slide was made, were supported by Tektronix's vendor for these things, which is Nexus. And I would guess that the parts that are TBD may not be. Their vendor, Nexus, really does a good job with working with people and tech in order to come up with whatever solution you're really looking for, independent of what type of package you've got. I need to make a couple of kind of notes here that things that are really important to keep in mind. A lot of these interposers, no matter which vendor, have significant lead times, like 3 or 4 weeks. So it's not something you can just at the last minute say, oh, I need that tomorrow. Let me call tech and see if I can get one. If it's a really standard one, you might get it, but you might also need to prepare for 3 or 4 weeks of lead time. And the other thing, which I think I have a slide, no, I don't know what happened to it. As you can imagine, there needs to be a certain amount of space around between chips in order to get the probe actually to fit in there. And so the second thing you need to keep in mind is make sure you have enough space on the board to use whatever interposer you want to do, which is another reason to call your vendor ahead of time and get a dialogue going on what the keep out area is and the lead times. Now let's talk just a little bit about logic analysis. Basically, I'll tell you what it's for in a minute, but these are examples of interposers, as I mentioned before, that are meant to go into a DIMM slot or an SO-DIMM slot and basically give you a place to put the memory card and then provide cables that will go to your logic analyzer so that you can see everything on the 72-bit wide bus. Logic analysis is really a tool that's used at the protocol level, not at the physical layer, and it has to do with diagnosing driver software, issues with timing, and protocol decode, those sorts of things. And a logic analyzer has a state mode in which you add a piece of software called a decode software, and then when it captures some data, it will go through and pick out what actually was going on. In this case, it says we have an activate, bank 5, and row address 113, a recharge, and now we're going to do a read to that same bank and address, and here's the data that came back. If I'm looking at rise times, I don't care at all about this data. But if I'm trying to debug software or a problem that might involve the physical layer or the protocol layer, it might be really useful to trigger on a particular data value that came back, and then perhaps have the logic analyzer or the MSO trigger the scope to see what actually was going on a particular line. The other mode that a logic analyzer has looks a little more like a scope. It's timing analysis. Basically, the difference between this and an MSO is that you can have all 64, 72, whatever lanes displayed, and you can look at the timing relationships between everything. What we've really done here is traded 8 or 10 bits of resolution on a channel for a single bit on each channel. So all we really know is whether a line is high or low and roughly how they're positioned with respect to each other. Now, I said before that an MSO is kind of like a logic analyzer. It basically will give you this kind of a display. An MSO may or may not actually provide the kind of decode that you would find in state analysis, because sometimes it takes more lines, and also it takes more sophisticated software than you typically need on a scope. Okay, so we've talked about logic analysis. I'd like to summarize a couple of things before we talk about products themselves. One of which is that, as I said, there are really equipment and software available to analyze any of the current DDR technologies that you might be having problems with, and to make precise compliance measurements if that's something you need to do. But it's really important to plan ahead, particularly when it has to do with probing the signals, because not only do you need to make enough space for the probe, but you also need to allow enough lead time to get the probes in-house. Okay, let's switch gears and talk a little bit about what types of scopes you might find out there to make these measurements. These are a couple of high bandwidth scope options, both of which would allow you to look at the fastest DDR4 signals that you might run across. And there are higher bandwidth scopes than this actually, but this really covers the high end of what you might possibly be doing with DDR4. And the other thing to keep in mind is the active probes that would be used to look at the signals themselves. Both scopes actually come in an MSO technology with an option if you want to order it. This is the Tektronix MSO, and on the front you can see the place where the digital cables are connected. And we talked about these BGA interposers already. These are lower end scopes which are more than adequate for looking at DDR1 and DDR2, and in a pinch, maybe DDR3. You just want to get a sense of some timing relationships between a couple of signals. 4 gigahertz is kind of marginal for looking at a 3 gigatransfer per second signal, but you might get some useful data out of it. Certainly usable for looking at 1600 megatransfers per second. One thing to keep in mind with these scopes is that they typically come with a what they call a high impedance probe, which is not an active probe, and they're fairly inexpensive. Those are really not suitable for looking at DDR signals, except maybe old DDR1, because they have fairly high capacitive loading, and they're going to really distort the waveform you're looking at. So even if you're going to use one of these scopes, you want to buy or rent an active FET probe of 4 gigahertz bandwidth or so to look at the signals. This is an MSO version. This is an MSO version over here. They come both ways. And I think that's about all I need to talk about on the scopes. And now we're ready for Q&A, right? So if anybody has any questions, feel free to type them into the chat area and we'll cover them. But while we're waiting, maybe I answered everybody's questions. Hopefully I didn't put you all to sleep. Let me pose a couple of questions that I've heard before. And one of which is, so those BGA probes really look like a pretty neat solution, but how would I go about installing one of them? It's not really something that you can do with your soldering iron or your wife's blow dryer. It really requires a BGA rework station. And if your organization doesn't have one, there are lots of vendors out there that have rework stations who are fairly familiar with putting the probes, to putting a sandwich down like that and getting it soldered reliably in place. Another question that I've heard before is, how do I know if the software that I'm going to buy for the scope is making accurate measurements? And all I can tell you, having worked at one of the companies for many years and understanding how they write the software is, and I'm sure it's really true of both companies, they have a team of people who, that's what they do all day, is they look at compliance test specs, they figure out how to make measurements that are in the spirit and accurately related to the measurements, and I'll just have to look at it in a minute. And then also try and make sure it really works right. And because they're there full time, if one of us finds something we question, they're happy to take the questions and either make changes if they did miss something, or if not, tell us why it actually is doing the right measurement. So do we have another question, Nico? Oh, okay. I did answer that question, yeah. And they might have one more question. I think we have time, or do we need to? I've forgotten where we are here. Okay. So we got one more question here, which is, what do I know about the BGA interposers and their impact on the signals I'm trying to measure? Actually, both companies have done a lot of work on comparing signal fidelity with and without the interposer installed, and I think they've demonstrated that in terms of perturbating the signal getting between the board and the chip, they really don't have a major impact. As I said before, the ones with the wings on them may show you a signal that's not quite as sharp as you would see with the smaller interposer board, but those are pretty minor, and you can also eliminate a lot of those slight differences by using an electrical model to de-embed the effect of the interposer itself. Okay, so I'm kind of at the end of what I wanted to say. I'm going to pass it back to Nicole, who's going to do some wrap-up here.
Okay, thanks, Tom, so much. So I wanted to mention, if anyone is interested in getting price and delivery or having one of your local representatives contact you to help configure a system that's going to best meet your needs. Rental pricing is really determined based on what your application is and all the components needed. We do have bundled solutions that are in stock, but here is a list of the local team that's on the East Coast. You can feel free to contact them. And then, Nico, if you want to go to the last slide. Also, you can request pricing delivery on our website at microlease.com, contact us. And in a few days, you're going to receive a survey. We'd like to do more of these, so we hope that you found it really valuable, and we'd love your feedback so we can do more in the future. And if you fill it out, there'll be a chance to win an Amazon gift card. And you can look for more upcoming events at our website, microlease.com, resources, events. And I'm Nicole Crossman. I'm at nicole.crossman@microlease.com. Feel free to email me as well with any questions or inquiries. Thanks so much for attending.